This video discusses Newton's first law of motion. So we commonly define Newton's first law of motion as a body in motion tends to stay in motion, and the body at rest tends to stay at rest, unless acted upon by an outside force. So this is really restating our definition of equilibrium. If the net force is zero, speed is constant. Newton himself wrote, although this is translated from Latin, because that was what you did back then, you wrote things like this in Latin, is that every body persists in its state of being at rest or of moving uniformly straight forward, except insofar as it is compelled to change its state by force impressed. So what he's saying here, well, uniformly straight forward is physics talk for one direction, constant speed. And being compelled to change its state by a force impressed is a force acting on it. If there's nothing pushing or pulling it, it's going to continue in a straight line at a constant speed. Newton goes on to define inertia to be a resistance to a change in motion, emphasis on a change in motion. It's not resistance to motion, it's a change in motion. If I get a locomotive going, locomotives have a lot of mass, therefore they have a lot of inertia. Once it's going, it's very hard to stop it. It resists going into motion, and it resists changing that motion. So, before Newton came around, on the left we have Newton, on the right we have the guy who was around before he came around. This is Aristotle. So the Aristotle worldview was kind of held to be the correct one. So in this case, let's have Newton and Aristotle discuss about a thing that doesn't move on its own, as you will find out when you change apartments in college. Couches. Couches do not move on their own. And Newton will say this much, that couch will not move unless it's pushed. And Aristotle will say, yeah, I agree to that. And then Newton says, but once that couch starts to move, a force is needed to bring it to rest. And Aristotle, his opinion is, I disagree. The couch's natural state of motion is to be at rest. That's kind of the wrong view. Newton's on the right track because he knows that the force needed to bring it to a rest is friction. If I push a couch across a floor, there's friction between the couch and the floor that brings it to rest. So we're not used to thinking of things that are moving as continuing to move unless something stops them. So I've got a couple different examples here that I hope will illustrate otherwise. So let's bring up the first one. So back in 1977, two probes were launched by NASA out to the outer regions of the solar system. So these were the Voyager probes. Voyager 1's going at about 17 kilometers per second right now. Voyager 2's going at about 15.5 kilometers per second. And this illustration shows them moving outward from the Earth. And once they pass the last planet that they touch, they move at a constant speed. Right now, they're moving outward from the Earth, outward from our solar system, at that constant speed, and they'll continue to keep moving until they reach another star system, but that will be thousands of years from now. A more down-to-earth one would be this one. This is 1989. It's the Flyers versus Capitals, and I had to find this off YouTube, so the video quality is not the best. So right here we have Ron Hextall, the first goalie to ever score a goal in hockey, and here he shoots the puck at 106, and it's in the net at 102. So the puck traveled at a constant speed almost 200 feet down the ice. And that's mainly because there was no friction to stop the puck because, well, it's sliding on ice. And then one last one that's maybe even sillier than the last. Let me set this one up. To the left, out of the screen right now, is a car. Some guy's hanging out of the car with a bowling ball. Over here, we see the beginnings of a ramp. The bowling ball is supposed to hit the ramp and then do, I don't know, something silly. The problem is, the bowling ball has inertia, so it continues to move at the same speed as the car. So, when they drop the bowling ball, it goes up in the air, and it hits the car. Now, it hits the car because it and the car are moving at the same speed. So, and yeah, I'd like to point out that the car wasn't braking at the time. It's got its headlights on. So, yeah, hits the car because the car and the bowling ball are moving at the same speed. So, just to summarize, unless a force is acting on the object cannot change its motion. It's going to be straight line, constant speed. And friction and drag are two forces that make Newton's first law seem non-intuitive. So that's why Aristotle, when he sat down to think about things, he said not moving is the correct state for most objects. Okay, thank you. Good night.